back on it again. Day 7. Night owl shirt. Yes. Night owl shirt. Night owl theme. Night owl everything. Just night owled out. We'll do night owl. Night owl is so good. May I request benchmarks today? Yes, you can. Let's take a look. Also today is crabs. So I had to read the problem before we started because, you know, doing it in Rust, got to read the problem if it's crabs. A swarm of crabs, each in its own tiny submarine. I need that to be like the open graph image for like one day I will write a blog post on like how to solve day 7, and it needs to be just like Ferris and a bunch of mini little submarines. Okay, so basically the thing here is that we have a bunch of numbers, so a bunch of positions, just like we did, I don't know, yesterday, the day before, something like that. So basically what we have is like this test input, which I will pull over into our... So the thing here is that we've got like a crab in spot 16, 1, 2, 0, 4, 2, 7, 1, 2, 14. And then we have to figure out like what position they all need to get to, but in the least amount of moves. So the naive solution will be to just like pick all of the spots that start at 0 and end at whatever and range through them and then calculate how far away everything is and then add that number up and see what it is. So that's probably what we're going to start with. I saw there's also a Gauss distribution that we can do today. Crab paper. This input results in the cheapest possible outcome being 37. So let's start with that. Those will be 37. We don't have another thing to test. Okay, so we've got fishes. We don't need to pass in this number anymore, so I'm going to take this out of the arguments. The puzzle input here with the input that we have should return 37. Currently, we'll get rid of this and we'll do cargo test bin part 1. Couldn't find it because I'm never in the right directory. Professional programmer, never in the right directory. Right, we don't have a 0 to 9 anymore. We have a separated list. Let's get rid of this. Let's do, I guess we're going to do like a B tree map, right? We'll let mute map equals this. Map is going to be a B tree map of values. What? I guess just like, I can't imagine that it would be a U64 position here. Also, the input is comma separated, yes. So we're just going to store the position on the left, so like 16, and then the number of crabs on the right. The number of crabs will be whatever. Let's check our puzzle input, just scan it quickly. It looks like the only number we get up to here is like 1100, 1400 right there, but still 4 digits total. I don't see anything that's like 5 or more. So this can be like U16 or something like that instead. I doubt we'll hit U64 here for the values, like the number of crabs. I think the total number of crabs in the input that we just looked at, I mean, this can't be more than like 1,000, right? So maybe we do U16 here too. And we just say that's that. And then we do map.entry. We have to parse this first, right? So we're parsing these into U8s. This needs to be actually a U16. So we're going to pull in these numbers, comma separated. Is that a map of final position total cost? That is a map of initial position total number of crabs. As a B tree map where the first U16 is the first position of the crab. So a crab starts at like 16, or a crab starts at 8, or a crab starts at whatever. We could do this actually. I think that works, right? Did I mess up the way to do this? I guess it can just be a struct, right? Struct initial position, num crabs. And we can just like basically document our code by using types. So map.entry, the entry is going to be initial position. There's probably an itertools for this, isn't there? Itertools Rust. I think that's one of the most interesting parts of Rust type, tuple, and enum system is that you can sort of alias types into human readable names. Yes, definitely. The thing that I just did there, if you are interested, is called like a new type pattern. Because what we've done here is basically we've created a new type that is a wrapper around like a U16 or something, but it is effectively just a U16. So Rust new type pattern, basically just create a struct that is a tuple struct that wraps your value, and then you can do whatever you want on that struct. So you can do additional impulse. This really helps if you're dealing with like the orphan rule, which is you can't implement a third-party trait for a third-party type. We do this in Rust Adventure for a Pokemon ID type that is a KSUID that needs to implement like, I forget what the trait is called, but it's like to SQL from SQL X or something like that, or from SQL. So what I do is we take, instead of years here, we do a Pokemon ID, and inside, instead of an I64, we have a KSUID struct. And that allows us to do an impl for like to SQL on Pokemon ID, but use the KSUID like internals to do it. I prefer the struct my type U16 versus the option of type my type equals U16. So type alias is the thing that will do like this point here is just a tuple, right? It's basically the same thing. So you can pass it a tuple and you can operate on tuples and things like that. And it doesn't really stop you from doing things. But the new type pattern requires that you wrap your value in something. So you can use the new type pattern instead of the type alias pattern, which is the struct thing versus type thing. You can use the new type pattern to initialize a value with a struct that is a private struct. So that means you can offer through your API a set of functions that are the only ways to initialize a private struct type, which means that if you need to do something to convert something from like an integer to an ID or something like that, you know that the only way that you can do that is by using one of these like provided initialization functions, because the struct itself is private. So I think we have to sort before we group by for this implementation. Isn't B-tree map iter pre-sorted? Get an iterator over the entries of map sorted by key. Okay, so it is sorted. Perfect. Yay for using the right data structure. So we don't need to sort. Wait, that's not what I was looking for. Sorry, the question confused me because we're not actually iterating over the B-tree map. We are iterating over the input to collect into the B-tree map. But I guess if we just insert, that works too. So because it's sorted, we can do for, these are not fish, are they? Crabs. For crab in crabs, map.entry, initial position, crab.parse.unwrap. What are we doing for here? 16. Or insert 1 and modify b plus equals 1. You already parsed it? I did already parse it, you're right. Okay, so initial position crab's already parsed, or insert 1. So that should give us the B-tree map, right? This will have to be num. I think I need to put n modify first. Derive debug on initial position, orb. I think we also have to do equality for ord, right? It would be interesting to figure out how to parse non-values into other data structures. We've done that though. Like the thing that we do here, which is pull values in, right, via nom, is the way that you parse them into other data structures. It sounds weird because you expect that to be like a built-in part of the library or something like that. But you can just like loop over until you're at the end and just keep inserting that into like a B-tree map. Like we did that yesterday, right? Like we wanted an array. I didn't click the right thing. Let's go to day 6, lib. We did that yesterday, right? So we have this separated list, but we also just have this array here. And like we could manually do an iter here and do basically like digit tag as the parser, and just keep taking and taking and taking and taking, and then discarding, and then inserting that into the array instead. But it's basically, it's the same thing, right? There's no like special magic sauce to it. It's just build up the struct as you want it to be built up, or built up the data structure. Lib, this is a reference to the map used here after move because I'm debugging it. Can't leak private type because this is not pub. Okay. So we end up with 0, 1, 1, 2, 2, 3, 4, 1, 7, 1, 14, 1, and then 16, 1. Where's our input? So 16 appears once, 14 appears once, 7 appears once, 4 appears once, 2 appears 3 times, 1 appears 2 times, and 0 appears once. So we're good. Let's do num crabs now. I usually don't type things out this intensely, I guess. We can't do v.0 plus equals 1. Crabs 1. Mr. Krabs. Okay, so we're good. So we basically just dereference into the new type struct, which is a tuple struct. So we access the value inside of it with .0, and then we can use the binary assignment because now we're operating on the U16 type. So that constructs correctly. And now in our process function, we need to crabs.iter. We need to find the min and the max, I think. because the bounds here are going to be, I think we have to use min by for the moment. So because we have the new types, we'll use min by instead. And this will be, what is it, num crabs. And I think we can do the same thing for max by, right? Not found in this scope. Perfect. Puzzle input num crabs. So if we want to deal with this outside of the module, we do have to make the interior value public. Did I not make this a tuple? I thought that was a 2-argument function. I guess not. Expected closure that takes 2 distinct arguments. Yes, that's what I thought it was. So why is it complaining? Let's open this up a little bit. Expected tuple found struct num crabs. Oh, right, because we're iterating over the whole thing. My bad, because this is actually this, right? So we have a tuple, and the tuple is the keys and the values from the B tree map, not just the num crabs. And it all runs, and let's check min and max here for kicks. Initial position 0, 1, initial position 2, 3. That doesn't seem right. Can we do, is it sorted by the key? It's sorted by the keys, right? When we iter. So if we do this and we do this, we do that instead. We can do that instead. So initial position 0, initial position 16. So just a little trick, because we used the right data structure, that is the B tree map, which gives us the keys in sorted position already. The first item in the iterator is the minimum key value. The last item in the iterator is the maximum key value. So we get to just pluck the next one and then pluck the last one, and we're done. And we don't actually have to sort or do anything. Okay, so we've got minimum and maximum, and then for min dot dot max, I think it's dot equals max probably. Let's do this. Dot iter dot map position. So we've got min and max. This gives us the position. We should do, I guess we could clone this, right? We would be cloning it for every single time, which I guess is okay, but like we could do a reference too, right? We don't actually ever need to mutate crabs, do we? Now that I think about it. We don't even need to do this either. I think that'll still work for us. Something isn't working. Do we need to intuiter arrange? We unwrap this and we unwrap that because they both exist. What am I doing down here? Let me deal with that in a second. So we still have 0 and we still have 16. So basically all I did is I pulled the iterator off to calculate the min and the max. So now we still have crabs up here, and I'm not creating 2 iterators. I only have the 1. We also don't want that though. I did the same thing we just did before. Okay, so now we're just failing our test. What's the difference between .0 and .1 there? So if you look at the types here, because Rust Analyzer is working now, there is an initial position and a num crabs in this tuple. This tuple exists because we iterated over the B tree map. The B tree map gives us a tuple of key and value. So when we do .next, which is the iterator function implementation trait thing, we get a key and a value in a tuple, right? Because we're iterating over the whole thing. When we do .last, we get the same thing. We get a key and a value. So what we're doing here is we're saying take the first position in the tuple. So this is tuple access syntax. So .0 would be an initial position and .1 would be num crabs. Okay, so we're iterating over. We got every position. I'm going to call this goal position. Okay, so we've got the goal position, right? And then we're going to have crabs.iter, .map, key value, let total movement equals crabs.iter, and this is going to be .sum. So what we're going to do here is take the initial position, right? Let's name these because we need to take the initial position of the crab, and get the absolute value of subtracting it from minus goal position abs. So this is also one of the things where type aliases kind of come in to play. So like because this is a new type, we keep have to typing .0.0.0. With a type alias, you don't have to do that. Let the change in X position equal the initial position .0 minus the goal position. So this is going to be like a U8, right? Did I misspell this? Is that what it's telling me? Oh, come on. Rust compiler to the rescue. Okay, so the initial position could be greater than the goal position, right? Or it could be less than the goal position. So these need to be like as I32 or something like that, right? I'm just putting them in a larger type. Okay, so we're mapping over the initial position and the number of crabs. Was just going to ask if you needed to manually cast the nums to handle the negative. Yes, we need to manually cast the nums because we're doing subtraction here and we might go negative. We're immediately converting back to positive. And I'm using a number that is, or a number type that is bigger than the number that we're using. So I think what I'm casting like a U16 to an I32 should work just fine. All of these numbers, again, are less than 4 digits. So I think an I16 also would have worked. I just went up for safety, basically. And then I can go back later and deal with it. So dx abs. So this is the change, right? And then we need to do dx times crabs.0. So that's the amount that it's going to cost us. If we have a crab at 4 and it has to move to 2, that's a cost of 2. If we have 5 crabs there, that's a cost of 10. And these aren't the same. So I'm just going to cast this. Did I mess up? What did I do here? Is num crabs a U32? Is that what I did? I guess technically this is always going to be positive, right? So total movement is a U32. Anyway, I think this will bite us if we do a U16 here. Sum total movement is a U32. dx is always going to be positive. So if we make this a U32 and we do this as U32, I'm surprised abs doesn't convert. I mean, I'm not surprised, I guess, but it would be nice if abs converted. So this is totals. Is there any benefit in pre-allocating your arrays, iters, and Rust? I know some languages have trivial overhead for expanding things. There are cases where you want to pre-allocate an array. For example, when we were working with the ND array a couple days ago, it would prefer that we don't go kind of like into a vec into an array. So to get past that, well, okay. So the way that I'll phrase it is that you have 2 options, right? If you know how much memory you're going to require, pre-allocating that memory is going to be better, right? In space usage, in terms of complexity and whatever, right? If you can pre-allocate and you know how much you're going to use, then pre-allocating is going to run better, basically. If you don't know, then you're using something like a vec, in which case you are going to at some point potentially trigger like the requirement that you grab more memory, right? So like Nikki says, you don't have to pay the cost of expanding the heap allocation if you pre-allocate the amount of space that you need. It's a trade-off, basically. And the Rust compiler is also super smart. So I would say if you're concerned about the performance of something, measure it, change it, measure it again, rather than assuming that whatever you do is going to be better. As we saw earlier in Advent of Code, actually, when we switched from read to string to buffered line reading, it didn't really change materially the things that we were looking at. So it's always good, like whenever you're making a performance improvement, have your benchmarks, have your heap allocation profiling, have everything set up first, measure, make the change, and then test again. Okay, so we've got the totals, right? And the lowest cost that we have, it looks like 37. Is that the number we actually needed for our test? It is. So if we do, instead of collect, we do min, we get sum 37. Expected U64 found option. That's fine. I mean, we're just going to unwrap this because it has to succeed, but we're going to change the type to be a U32 because that's what we have. And we don't have any other constraints, so we can do whatever we want. Why min max are options? Because if you have an iterator of nothing, you get nothing from the min, right? If you have a 0 element iterator and you want to look for the smallest element, there is no element. Therefore, there is no smallest element. All right, let's get our actual code here, or actual input. Get rid of that. Input.text, cargo run, part 1. Okay, let's see if this is our answer. Hopefully it is. If it's not, then I did something wrong, obviously. Yeah, it's our answer. Crabs don't seem interested in your proposed solution. Perhaps you misunderstand crab engineering. Oh, I will defer to the crabs as a Rust programmer. I will let the crabs tell me what is correct. As it turns out, crab submarine engines don't burn fuel at a constant rate. Instead, each change of 1 step in the horizontal costs 1 more unit of fuel than the last. First step costs 1, second step costs 2, third step costs 3, and so on. As each crab moves, moving farther becomes more expensive. This changes the best horizontal position to align them all on. For example, this becomes 5. Hopefully that looks like the original input. So we're looking for 168 now. Let's copy this. We'll do new file part2.rs. Paste this in. We have the same stuff here. We have 168 is now the number that we're looking for. Oops. So let's cargo run or cargo test bin part 2 to make sure that our test fails first. And then we go back into here and we have to recalculate the cost. So we've got the differential here. And then this is cost is the differential. Is it just +1 each time? So it is 0 dot dot equals dx dot sum, right? Unsatisfied trait bounds. 0 dot dot dx dot sum. Cost is 1 + 2 + 3 + 4 for how many steps there are. Yeah, so we have the change, right? We have the number of steps, and then we just need to add them together. I don't know that that's an inclusive whatever, but this needs parentheses because, you know, it does. Consider giving cost a type. What if we put cost here? Can you infer the type for us? No, we cannot infer the type for us. Damn it. Can we do U32 here? We can do U32 here, and our test is passing. So that was it. We just needed to sum them up. This is going to be one of those things where it just runs forever because I wrote the wrong thing. All we added was sum, right? This will finish. When? Okay, there we go. I'm going to run it with the release build if this is the answer. But huzzah, that's the answer. So that's all we had to do, basically. Just sum them up and change the cost. Okay, so let's do benchmarking. Let's start off with the heap stuff because we already have the heap stuff implemented. Day 7 README. Yeah, I just thought it was a nifty way to express it. Yes. One of the things that you do get used to, Derek, as you use like more functional languages more, is having functions like that just like sitting around, right? Like a sum on an iterator is just a thing that should exist. And that eventually gets lodged in the back of your head. So if you have a thing and you need to add them all together in some way, you just sum them up. You don't have to like for loop and add everything together and whatever. And that, I think, realistically, I think that's the key insight of like, the key takeaway to functional programming in the general sense. It's that you can write things declaratively without having to like manually pick everything up. Which means that, hey, we just sum this together is much more readable than like for whatever in whatever, mutate this, add 5 to it or whatever it is, right? It's one of the reasons that I describe like understanding collect and how containers work with respect to collect. Like you can collect to a string, which is a container, but also like a vec or like a B-tree map or like whatever, like understanding how one data structure can transform into another data structure, and thinking in terms of the data structures and not the operations that it takes to get from one to the other is a really powerful thing that you pick up more and more as you learn more Rust and any functional language in general, actually. All right. So we did this target release part 1, target release part 2. I mean, we are using like 11, 14 kilobytes, and we're not changing. Like either one doesn't change. So part 1, part 2. Okay, so we've got the original solutions here. We'll do Criterion, I suppose, since I said that we were going to do that at some point. I do love the zero cost abstraction focus that Rust has, because it means that like I never actually need to worry about that. Or like not never. Like when we're doing Advent of Code, there was a couple days ago where we had to care about the runtime, right? But we fixed that by changing the algorithm, not by optimizing the representation of our structs and stuff like that. So like I really, really like being able to write high level code just like I write in JavaScript, but getting the performance that the Rust compiler is capable of giving and the optimizations that the Rust compiler is capable of making because of the whole type system and the ownership model and all of that kind of stuff. Criterion, right? That's what we were doing. We need 2 things. Criterion uses a custom benchmark harness. So we are going to need 2 things in our cargo toml for day 7. And these will be a new dev dependency of Criterion and a new benchmark. We're calling it my benchmark apparently, which is fine. I don't really care. But we're turning the test harness off. The test harness, so in Rust, there's a thing called the test harness. The test harness is when you have tests like we do in part 1, right? Or part 2, where you have config tests, mod tests, whatever. You have like a bunch of test annotations and stuff like that. The test harness is the thing that defines, that grabs all of those things in a binary. So it's basically a main.rs specifically for testing, and then decides how to run those. So when we turn the harness off, we get to use somebody else's main.rs to determine how to run our benchmarks. Apparently we can't compile because cargo is broken. Oh, right. Cargo is now checking to make sure that we have the my benchmark file, which we don't have. So let's do this. Benches is a special directory. So make dir benches, touch benches, my benchmark.rs. I'm just going to paste. Let's see if that worked. I really like new shell, I have to say. Like, this is so much more readable than like PB paste, like angle bracket. Do you use one angle bracket or two angle brackets? Like, which one appends, which one overwrites? This is just like, save it out to this file. And then you're done. Okay, so if we run cargo bench now, this should download Criterion and then not fail because I don't think we import anything that we don't need. So this is going to run a Fibonacci benchmark because that was the example, but it'll give us a second to kind of look at what Criterion actually looks like when we want to run it. So basically, there's a couple of things here, right? So there, we pull in the Criterion trait. The Criterion main is, I believe, the test harness. The Criterion group is kind of like the groups of benchmarks that we're running. Black box is really, really important. So black box is a way for us to say, hey, Rust compiler, do this work no matter what, and do not optimize it out, right? So it treats basically this function call as something that it shouldn't like dead code optimize, right? So if we never use the value that comes out of the like the black box function, totally fine, just run the code anyway. Whereas normally if we didn't use a value and we didn't use a function, Rust compiler would take that out of our binary and actually just not run it at all, which is really cool and really great for production use, but it's really not what we want when we want to run benchmarks. We want to run functions that we don't use at the end, basically. So Fibonacci 20 takes 25 nanoseconds on the lower bound, 25 nanoseconds, I guess, on average or mean. I don't know which one that is. And 25 nanoseconds at the high end, right? So we've got this kind of cool thing, which is like, we've got fib 20 and then times it took. So fib 20 is our bench function. And then we take our bench function and we're iterating over the Fibonacci, right? So where is my code? So we do this in part one. I wonder if we can do this through crates. I don't actually know if we can pull this function out of part one. We might need to put it in the library. Yeah, I don't think we can reach into the binary to do the testing. So we have to take this function and we have to move it. We're going to name it process part one. I'll put this in here, process part one. In lib, I will drop it in here. It'll be pub function process part one. So we have to change the way our code is organized a little bit to be able to do this. We don't have a couple of imports here anymore because we're just pulling in the part one processing. This test feels a little weird to have in here now, right? So we're going to take that and we're going to put it in lib. This is going to be part one. The pre-allocations were making me use a bunch of usizes. So cutting that piece out took 7,000 bytes. Yeah. So if you pre-allocate space you don't need, you will pre-allocate space you don't need, right? Let's see. So let's do the run here again, just so that we have our build happening. I don't think that matters actually, now that I think about it. So here's our function, right? This function takes the input and does whatever. We're gonna black box, I guess let's do the full input, right? Let's do the input.text here. Const input, you're supposed to do input all caps here. So I'm gonna do that. Include stir input.text. Great. And then we're gonna use, I guess this is gonna be called day 5. Ignore the fact that it's called day 5, sorry. And then we're gonna call process part 1 with a black box on input. And this is gonna be part 1. So if we run cargo bench now, it should run that a bunch of times with the release profile and stuff. My hope when I requested benchmarks was to see the part 1 and optimized part 2 take the same amount of time. Oh, so you already, okay, I see what you're saying. So this takes 7 milliseconds. Is that because we have the debug on in our release, I feel like it should take less than 7 milliseconds for part 1. So you mean the optimized part 2 as in like the mathematical approach to part 2? The Gauss distribution or something like that? Cool. I don't know how to do the Gauss distribution yet, so we have to go look that up. Okay, so we're looking at... Oh, also one of the things that Criterion does that I totally forgot it does, which is absolutely amazing, is like, so it gives us this part 1, right? And then it gives us the time that it ran, and it gives you the change, like the percentage change. But if you make a change and you keep running your benchmarks, like I was saying before, if you run it and then you make a change and you run it again, you can see how much change there actually is between the two by default. So we just got 8% better by removing the debug from the release, which we need the debug from the release for the heap profiling, but you know, and now we're seeing like basically the same. And we'll be back tomorrow, same time, I think, like 10 a.m. Yeah, 10 a.m. tomorrow, same time. Have a good rest of your day, y'all.